Hello, everybody. Welcome back. In this lesson, we will go over the concept of absolute or global extrema. First of all, let's try to understand what do we mean by absolute. A better meaningful word, we will use both of these words interchangeably, but global, when you look at global, that pretty much tells what it is. It means it's a universal quantity. It's universal, and extrema does not mean anything except for maximum or minimum values. So we have already seen when you consider a function, for instance, like let me give you a graphical example on this form. Now, when you consider this kind of a scenario, let me give a couple of numbers, right? So let's say this corresponds to 1 and this value corresponds to 3. This is some kind of a function. And when you consider this window, we all can see here, let's give a value for this one too. Like let's call it 4 and let's call this one -3. When you consider this combination, you can clearly see there's an extension for this function. It doesn't stop. Now, when you consider these two windows, for instance, right here, we know right at this point, this is a local max. And what you see here is a local minimum. Sometimes we call them this local, interchangeably we call them relative minimum. Local maximum and local minimum, or in other words, relative maximum or relative minimum, which means it is relative to, it is measured relative to that neighborhood. However, when you consider this value, this value here, it is not the biggest value that this function can attain. If you walk over this function, if you keep walking, if it is a hiking path, once you get to this level, you can have a better view, right? So it's going to be grand compared to the previous height. So that simply tells us there are values that can exceed this height. So it is not, 4 is not a global maximum. On the other hand, -3, which is a minimum of this local in that neighborhood, it's not going to be a global minimum because there can be other values that can go below -3, something like this. So this simply tells us an important variation of these extrema. We can consider absolute or global extrema. On the other hand, now think about this scenario, compare it with the situation where we looked at the function earlier in early applications. When you look at the function of 4x divided by x squared plus 1, for instance. If you recall plotting this function, if you recall the graph of this function, it looked like this. Extrema occurred at -1 and +1, and those two corresponded to -2 and +2 in particular. Now, if you look at this function, what is the biggest y value this function can achieve? It is none other than 2. What is the smallest y value that this function can achieve? That is none other than -2. It cannot go beyond those two boundaries. So in this scenario, you can say at this particular point on the graph right here, it's a global max. It's not a local maximum only. Of course, it's a local maximum. When it's a global maximum, it's a local maximum. And then you can say something beyond. Global condition tells us something more than a local condition. So this is none other than a global minimum. Sometimes interchangeably we will say absolute minimum, and absolute maximum. So this scenario tells us something specific. For certain functions, you can have a global maximum and a minimum, or global max, or one of them, or not the other. Or certain functions may have local extrema but not global extrema. However, if you consider this example, let me just move this one a little further, and let's analyze the first example a little more. If you look at this scenario, what if you break this into a certain small interval, right? So what if you consider this particular function other than considering it? Okay, so let's have a variant of this entire problem. Just by giving, okay, so let me fix it a little bit. Look at this kind of a scenario. I'm going to draw the same function, pretty much almost the same, but I'm now going to draw it on a restricted domain starting from 0 all the way up to 0 up to 4, I would say. So let's say at 0 it's somewhere, and then at 1 we know it corresponds to 4 on y-axis, and at 3 we have this value, and let's say according to the way we defined, at 0, at 4 it's going to be just 0. Now, if you restricted the domain, if you cut some of the pieces of this function, and if you restrict it to a smaller domain, now this has the hope for global maximum and global minimum on that particular interval. So because of this reason, we can analyze this kind of a scenario. Now, what are the global max and min value? In this case, it's going to be right here. Now it's a global max, and this is a global mean. However, if we extend this interval a little bit, now this is example number 2, right? Let's say this is the second example. And what if we draw another one? Let's make a copy of the same. And let's look at this scenario exactly with the same behavior, but now I'm going to extend this half a little further. Now I'm going to place my endpoint here at -3. Let's say x equals -3. And suppose it corresponds to -4. Now, if you look at this scenario, if you look at the global maximum, the global peak, it remains unchanged. It's exactly the same. There is no y value that can defeat that maximum. However, on the other hand, the previously considered minimum is defeated by this one now, because the function went little beyond to catch something much more negative compared to -3. So now it is -4. So now in this case, we can see the global minimum is not here. The global mean occurred at an endpoint. So the global minimum can occur not only at a point where you have a critical number. On a closed and bounded interval, it can occur at an endpoint too. So all you need to keep in your mind in this consideration. Now, all of these are illustrations. However, when we jump to an example, right? When we dive into an example, you will see this idea gets really practical, and you do not need to worry about any of these illustrations. It has a very simple algorithm. So this entire explanation is just to help you to see what's going on. What is the significance of this new concept? Now, let's start with an example. It's this simple. Find the global extrema of this given function on the interval -3 to -2, and then -3 to -1, -3 to 0, and -3 to +3. Now, let us see how we're going to deal with this. The first thing, now we are going to analyze each and every of these cases separately, right? Each and every of these cases would count for a separate problem. Now, the first thing that we need to do is to figure out the critical numbers, because no matter what, it could occur at an endpoint or a critical number. So we already have the descriptions of the endpoints when we have the intervals. However, we need to look at the critical numbers. That information is coming directly from the function itself. So that is what we are trying to do first. First of all, take the derivative, and we know the derivative is going to be 6x squared minus 6x minus 12. This is pretty similar to previous examples that we worked with, so this is not a surprising computation, and this will leave us that is the derivative computation. First you factor 6 out, and then you factorize the rest just by quadratic factorization. And then when you do that, you end up getting this. Now you have critical numbers. X equals -1 and x equals -2. Now, look at these numbers. You have two critical numbers. And each case, the function has its own domain. Now, in this case, when you work with part A, this is the domain of the function. So now let's consider this the part A here. Now to consider the answer for part A. When you consider this interval, and if you compare these two critical numbers, are these critical numbers living in this interval? In fact, the second critical number has an error. It shouldn't be a negative value, it should be positive, right? It should be +2 because it's coming from x minus 2 equal to 0. So x equals +2. Now, when you consider these two critical numbers, are those two sitting inside this interval A, interval given in part A? No, they're not living in that. For that case, what you need to do is just to consider these two endpoints. This scenario is just like this. You have a function either decreasing or increasing, right? And there are no critical numbers in between. So if you try to find the global extrema, all you need to do is to determine the values of the endpoints. So that is exactly the scenario we are working with. So the simplest work that we need to have is this. We need to consider x values, and we need to consider the function values at those points. But what are the x values we are going to include? Now, we do not have any of these in this interval. Not -1, not +2. Therefore, what we're trying to do is to consider only the endpoints. That would be -3 and -2. Now we try to compute f of x. Let me do that computation separately. And that computation starts with exactly the definition of the function, right? You need to go back to the definition of the function. You need to do this computation. So it is computational no matter what. F at -3. That means you plug in -3 in the position of x. So what you're going to get is 2 times negative 27, it is 3 cubed. That would be negative. That would be 27. Since it's negative, there's a negative sign to comprise that. And minus 3 times 3 square. So it becomes positive 3 square. In other words, it's 9. And then you have minus 12 times x, and minus would make it plus because you are including negative 3 in the computation. That will be the 36, positive 36, and then plus 5. And let's compute this carefully. Now here you have two copies of negative 27. In other words, it's negative 54. And here you have negative, again, 27. And then you have 36. And you can just do the computation right away. You can employ a calculator for this if you would like to use a calculator. If not, you can simply just play with the numbers, right? So it's not just complicated, right? So when you consider these two, you can clearly see it. Okay, so negative 54 plus 41, it's going to be negative 13 at the end. Put it together with this, you're going to end up getting negative 40. So the value that you're going to include here is negative 40. And then you need to compute the value at negative 2. To compute that, again, you're going to do this, negative 2. 2 times negative 8 now. And then minus 3 times 2 square. So it's going to be 4. And then include negative 2 there. So that would make it positive 24. And then plus 5. Simplify, simplify. And you're going to get negative 16 minus 12 plus 24 plus 5. So we can see this would count for negative 28. And with this, it's going to be negative 4 plus 1. It's going to be just a positive 1. So that brings us the second value. That's going to be just positive 1. Now, all you need to do is now all of this work that you see here is, I mean, this is not necessary as far as you do the computation properly. And then just get rid of this. This is just simple kindergarten algebra or arithmetic even. So just get rid of that component. Now all you need to do is to compare these values. Which one is bigger, which one is smaller? So the bigger value is going to be the global max, and the smaller values, of course, negative 40 compared to 1 is the smaller value. So that's a global minimum. Let's consider part B now. In part B, we are going to do the similar practice. We are going to have the similar practice. Let's do this, x and f of x. And the only difference is now one of the endpoints coincide with one of the critical numbers that we consider, right? Right now. So it's not going to be anything new. We are going to pretty much do the same thing because the endpoint and the critical number are going to match and there is nothing beyond. And at negative 3, we already computed it's negative 40. And then at negative 1, what is the function value we end up getting? When you plug in negative 1, you're going to get, let's do it right here. It should be convenient. So it's going to be negative 2. When you plug in negative 1, you're going to get negative 2 in the position of the first term, and then minus 3, and then plus 12, and then plus 5. We can clearly see the first two terms will cancel with the last, and then leaving just plus 12 in the consideration. So it's going to be 12. Clearly, one can see this is the global max. and this is a global mean. And then once you know the global max occurs right here, right? This is the global maximum. And if somebody asks you where it occurs, it is none other than the corresponding X value. So whenever we consider a maximum value, it's always good to answer both of these questions. But when you present your solution in this form, like a summarized form, everybody knows what you're talking about. Now, why is it necessary to have both of these pieces? Think about this. If you're running a real world scenario, if you're considering a real world scenario and you pretend that you're running a business, you have a production level or certain parameter in your production. And when you vary that, you're trying to get, like, let's say, a profit. Now, if you would like to maximize your profit, you need to recognize the change of the parameter. How much should you change it to, which value you should fine tune it to. So this is that value, the value that's in your control. That is the independent variable. When you do that, how much of profit can you make is exactly the independent variable. So that's why this kind of a consideration is really meaningful in real world setting. You need to think about both of these variables, both of these parameters. All right, so now let's consider part C. When you consider part C, you can clearly see this critical number, right? The critical number that you consider in the left, I mean, the small critical number, it's sitting in this interval, but the other one is not in consideration, right? It's out of the ballpark. So what we're trying to do is now in this occasion, x, f of x, and we have -3, and we need to consider the critical numbers, all critical numbers that lie inside that interval, and the endpoints. If you consider these two, these are endpoints. And this one is a critical number. So whenever you consider this interval, you always need to consider the endpoints. You need to include both endpoints, and you need to include all critical numbers that would sit inside that interval. Now let's compute the values. -40, +12, we know those two values, and then you can plug in 0 also in the original expression, and we know the outcome. This will disappear, leaving just the last value, which is going to be 5. So we know. Now in this scenario, what are the global max and global min? Global minimum is right here. Global max is right there. It doesn't change. It's pretty much the same description as before. So it is pretty much the same. All right, let's consider part D. For the next one, you consider from -3 to +3. That simply means you're going to include -3 as one of the endpoints. And then you have -1 and +2, both of them included in your consideration, and then +3 as the right endpoint. So in all cases, look at this again, end, these two are end, and these two are critical. And then let's compute. This is none other than -40, 12, and then at 2, what do you get? You need to do that computation now. Let's go back to the function and do it. Let's plug x equals 2 in this expression, and let's compute it, and you're going to get 2 times 8, that's going to be just 16, minus 3 times 4, -12, minus, plug in 2 right there, so -24 plus 5. Simplify it, and you will end up getting positive 4 plus 9 plus 5. It's going to be 9 altogether. I guess even I made a mistake in that computation. Do you see it? No, this is completely incorrect. So that means be careful when you do computations. When it comes to easier stuff, there's a high possibility that you're gonna make mistakes. So pay attention to small computations. Here you have negative 36, right? And then with these two you have uh, positive 21. Positive 21, negative 36. One can see it is negative 15. Okay, here you go. When x equals 2, when you plug x equals 2 in this function, what we are going to get is that. So negative 15. And then let's consider positive 3. Now, some of them could be computational, but these computations are not going to be too overwhelming, right? So positive 3. Let's input this and let's see what it's going to spit out of this function. When you plug in positive 3, you know it's going to be 27 times 2, it's 54. And then it's going to be 3 times 9, it's minus 27. And then minus, now when you plug in 3, you're going to get 36 and then plus 5. And now simplify. Here you can see it turns out to be positive 27 and then positive 27 plus 5. That's going to be positive 32 and then minus 36 will result to negative 4 at the end. You can do the computation in different ways just to verify and just, I mean, this is not calculus, right? It is just simple arithmetic. So be careful when you perform simplifications and try to do it carefully. All right. So with that, we do have exactly the value. So let's bring it down to what we have here. Now, once you have it, now you can see, now you can compare them, right? Which one is the global max? Or sometimes we can call it absolute also, right? Still, this is absolute minimum. Absolute maximum is right here. So check your computations. Again, do not just trust my computations, just double check and see if those would give you the same values. So with that, we can see this is yet, now these two values, look at this value and that, these are negative, but those are not negative enough to beat this absolute minimum. So if you look at this graph carefully, what's happening is here, these two are critical numbers and those are the local maxima and minima this function can attain. However, the endpoints, one of the endpoints managed to beat one of those local extremas. On the other hand, this value is not positive enough to beat the top value, the absolute maximum. But I recommend you to think about this scenario. What if you consider this interval, negative 3 up to 5? What would happen? Then you would replace this number 3 here by 5. And then when you compute, you may end up getting something that actually can be used to beat this value, the maximum, the absolute maximum value that you see on the current interval. So now, when you look at this problem, if you have like some kind of a confusion, how this is working, right? Because in a problem, are we going to get different scenarios like this, like couple of different intervals? No, it is not the way. In a problem, usually you will be given one of the intervals. It may be asked like, okay, find the global extrema of this function on this interval. On the on the interval, on the interval, this is just like on just -3 to +3. So in that case, you're going to do exactly that analysis only based on that interval. Here I included multiple scenarios so that you can see a variety of options in your computations. However, it includes more than what you need to handle all of these problems. Now, the next step is like, look at this. This is recalling exactly the graph that we had right at the beginning for the illustration. Now, you may have an impression already when you worked with the previous example, we always need to have finite or bounded intervals to get to uh, absolute extrema, to have absolute extrema, which is not correct. They can occur even on the entire real number line. Sometimes when you consider this kind of a scenario, I'm not going to compute all the technicalities behind this problem, but we know already the graph. We recalled it at the beginning. It looks like this. In this scenario, you can see the global extrema occurs right at +1, which happens to be 2, and it happens to be at -1, it's going to be the global minima, which is going to be -2. Both of these values are defined, are beating all possible outcomes throughout the entire interval from -infinity all the way up to +infinity. So that can happen, yet it is about absolute extrema. So do not let these examples mislead you. The situation where you need to consider absolute extrema, it is not only about like a um, closed and finite interval, right? So in this scenario, it could be like even the entire real number line. However, now this brings us to a conclusion for this particular section. And what you need to understand is simply the concept of global extrema. The global extrema is simply the extremum values that the function can attain that cannot be beaten by any other value. So that those are just pretty much universal maximum values and minimum values that you can expect from that function. They may occur, they may not occur, depending on the situation, right? So if we consider, if we go back to the very first example or the illustration that we had right here, since we do not have a bound for this function, there is no hope for global extrema, because always in the right end, the function will be rising. So there will be no global maximum and there will be no global minimum as far as they continue from each end. So global extrema cannot happen always, but whenever it happens, it's worth finding, because sometimes they are heading towards certain applications such as real world scenarios, profit of a business, minimization of a cost of a business. So when you consider these kind of scenarios, nobody is going to ask you what is the local maximum profit or local minimum cost. One would ask simply, what is the maximum profit of your business? What is the minimum cost of your manufacturing process? So when somebody asks that, they always talk about the global phenomena, not the local extrema. It is real world applications are about global extrema. That's exactly the reason we are curious and we are interested in investing on global extrema. So with that, we come to a conclusion of this lesson and try to understand it is a very simple computation. All you need to do is to compute the critical numbers and grab the interval that you're working with and plug in all the endpoints and the critical numbers that are already living in that interval into the original function and compare the values. Which value would give you the best option? Which value gives you the biggest outcome and the smallest outcomes? And then in that way, you can determine the global maximum and the global minimum. All right, so we will bring this to the next level where we are going to have some real world applications in terms of optimization problems. See you on the next lesson and enjoy problem solving.